So in this session, we will look at a different problem. We have seen enough of vertex cover. So we're going to look at feedback vertex set problem and try and design a fixed parameter tractable algorithm for the problem. Okay, that's a problem. So have you seen this problem? NP completeness approximation? No? Yes, no, no, they're not. Okay. So what is the problem? Your input is so again it's an undirected graph, but there is also a same problem version of the problem in directed graphs, which is considerably harder, but we will look at only the undirected graph version. The question is something similar to vertex cover. Is there a subset of vertices such that G minus S is a forest? You have not seen this problem? Okay. So in the case of vertex cover, you want G minus S to be no edges. Here we are saying no, so that means no cycles, right? Because a forest means it's acyclic, right? So I want a subset of vertices whose deletion makes the graph a forest, which means this, in the case of vertex cover, the set of vertices were covering edges. Here the set of vertices are covering cycles. Okay? And as I said, there is a version of it in directed graphs also, but here we are talking about undirected graph. Okay, so now let's start the base case. Given a graph, can you check easily whether it is a forest? How do you come up with an algorithm which will test whether a graph is a forest? BFS, DFS or something, find all the components, and then what are you checking in each component? Whether it has a cycle or not. Can you do that easily? Yeah. So how will you detect a cycle? Yeah, if you find a back edge or something like that, right? So you can detect, there are enough number of algorithms using which you can check whether a graph is a forest, whether it contains a cycle or not. In fact, a more challenging exercise is to detect whether a graph is a cycle in order n time. Okay, so I'll leave that as an exercise. Independent of m, okay. Regardless of the number of edges, I am saying that you can actually detect whether J has a cycle in order n time, okay. But that's a next level exercise. But the important thing is you can check in polynomial time, right? BFS, DFS, linear time, and then look for back edge or something. So some easy algorithms to check whether a graph is a forest. So now I am asking the question: can you delete k vertices and get a forest, right? This is one of those deletion problems. I mentioned this hereditary property, can you delete k's? It's one of those such problems. Okay. So what would be a brute force algorithm for this? Okay, it's always a good starting point to know what your benchmark is we are trying to improve, right? So what is a brute force algorithm for this? Yep. Try all subsets of size less than or equal to k, delete it, check whether the remaining thing is a forest, which I just told you that you can actually do it in linear time or something. Yeah. So what would be the running time of that algorithm? N power k plus 1 kind of algorithm, right? So basically try all subsets of size at most k, and this gives you, n power k plus c kind of an algorithm, or c is some constant, right? N power k plus 1, and then each time you have to go and check whether there is what remains is a forest, right? So this is not a good algorithm in our framework because k is sitting on top of n, and I want to know, can I drive k out of n and get an algorithm of the running time f of k times polynomial in n. Okay. So if I want to come up with something like what I did for vertex cover, cluster vertex deletion, deheating set, what should I do here? What is the abstraction set I have to branch on? Cycle, right? So find a cycle in the graph, which you can find easily because you can check whether there is a cycle in the graph in linear time. If not, it will give you a cycle. You can find a cycle in the graph, and then what do? Which one? What is the strategy we've been using so far? Try all, because anything more clever, you need to be very careful about it, look at the overall structure, argue about it, and so on, right? In some cases it may be possible, some cases it may not be. So if I am looking at some general instance, find a cycle, like we found a P3 and we said, I don't know X is the correct choice or Y is the correct choice, I'm going to try all, and gave us a three-way branching kind of thing. So here I will just pick, I don't know what is the correct choice, I will take a cycle and say, if I have a find a cycle like this, then I will try one by one, delete this, recursively check whether the remaining graph has a feedback vertex set of. So feedback vertex set is this solution size, the solution set. Okay, it has a name called feedback because it is connected to some feedback registers and so on about in electric circuits. So you want killing a set of vertices which is covering all the feedbacks in some sense. Okay, so I am trying to find a set of vertices, a deletion set to make it a forest. So in this case, I will try one by one. I will try delete this and then recursively look for a k minus 1 size solution, delete that and try all of them. Okay, but what's the problem here? What, does that give you a good algorithm? Size of the cycle plays a role because in the case of vertex cover it was 2, in the case of cluster vertex deletion it was 3, in the case of deheating set it was d, but here I have no control on the size of the cycle because that contributes to the branching factor. So if the cycle length is root n, then I will get a root n power k algorithm. So I have not really driven my k out of n because instead of n power k it becomes n power k by 2 or something, but still it's sitting on top of n. Okay, so I don't have somehow if I can control the length of the cycle to some constant, then I am in the game. I can do the branching like the way we did, right? But we can't guarantee that. So what we are going to do is to do some pre-processing first. What are some simple pre-processing we can do? Like we did for vertex cover? Isolated vertices, get rid of them. Degree 1 vertices, what do you want to do? Delete them, right? Because they are not covering any cycle. It's not like for vertex cover you pick the neighbor, no, you just delete them. Because I am trying to cover cycles, nice degree 1 vertices are not going to cover cycles. So we will have rule 1, delete vertices with degree less than or equal to 1. Okay. Now what do we want to do with degree 2 vertices? So I have a vertex whose has exactly degree 2, but y may have lots of things, z may have lots of things, they may be adjacent. Can I do something with degree 2 vertices? They could be part of cycles, But notice that any cycle x is part of, y and z are also part of the same cycle, right, because x is degree 2. So, x is not going to cover any more cycle than what y and z can cover, because anything which x is part of, any cycle which x is part of, so y and z are also part of it. So, should I just delete x? I should choose x. No, that's not a wise strategy, right? Because x is not really doing so much job. I could actually choose y or z. But you don't know, x may not even be part of a cycle, so there are all possibilities are there. Somehow I want to pre-process it and maintain the cycle structure. I mean, I could just delete x and say, hey, y or z will do the same job as x. But that has some other problem. What problem? The cycles that existed may go away and you've lost your cycle property, right? If I delete x, saying that x is of no use because y and z can play the same role, but the problem is then there was a cycle that contained x, y, z, then that would have vanished and you would have left it uncovered. Okay. So here is, in fact, if you've seen the approximation, or you have not seen approximation for feedback vertex set, here is a popular reduction rule to deal with degree 2 vertices. If x is so in this case, then you do what is called short circuit, as basically we will delete x, but we will add y and z, which means you can think of it as I am replacing this by a direct edge between y and z. So it's basically I'm short circuiting. So anyway, any cycle through x should go through y and z. So instead of deleting x and not doing anything about it, I will delete x and make y and z a direct edge. So that means all the cycles are preserved. If yz was already an edge, I will add a multi-edge. So it will be a multi-graph. Okay. So what I will always now have a multi-graph, because then this is a 2 cycle. I need to maintain that cycle structure. Right. So always when you design rules, you have to how do you prove correctness? The way to prove correctness is that if I have a k-size solution here, if and only if there is a k-size solution here. That's what would prove correctness, because that means I have not lost any generality by doing these rules. Okay. And in fact, that needs to be proved, but it's at least intuitive what I am doing here, right? Question? No. Okay. So fine. So this is a rule I'll do. Okay. Now it's possible. What happens to a cycle? Suppose the whole graph is a cycle, and if I keep doing this rule, what happens? Because whenever I have a degree 2, I will short circuit. That becomes a degree 2 short circuit. Eventually, I will have a loop on a vertex, right? So let's say I'm working on multi-graph. That means I'm allowing multi-edges and loops. So if a vertex has a loop, what can I say? That is a cycle of length 1. That needs to be covered as well. Who will cover that cycle? Only that vertex. So include it in the solution, right? That's rule number 3. If x has a self loop, include x in solution and k is dropped by k minus 1. Okay, so that's all I'm going to do. So what I'm done is basically I have done something with degree 2 vertices and degree 1 vertices and degree 0 vertices. Okay. What is my aim? My aim is to somehow get a short cycle. If I have a short cycle, I know how to branch and get on to my old strategy or whatever I have been doing of branching, right? Is that clear? So what is now after doing all this, the resulting graph. So this is all polynomial stuff. What is the resulting graph? What property does it have? So I have G prime, K prime. What is the property of G prime? We did some rules to simplify it. So what? Sorry, I didn't get it. Loopless, okay. What else? No degree 0, no degree 1, no degree 2 as well. So the minimum degree in G prime is at least 3. Right? Because all I have done is dealt with degree vertices degree 0, 1 and 2. Minimum degree is at least 3. So now you can pull out a nice theorem. It's called Herative theorem, and it appears as a problem in your problem sheet, which is any minimum degree 3 graph as a cycle of length at most some 2 log n plus 1. If, okay, I should correct it, maybe we should fix it in the problem sheet. If it has a cycle at all, actually it should have a cycle because minimum degree is 3. Because if it's acyclic means it's a forest, forest means there will be leaves, there will be degree 1 vertices, so it's fine, okay, fine. So this is, because remember our goal was to get short cycles, right? Because if you have a short cycle and if you can find it fast, then you can branch on it and you get a reasonable FPT algorithm. That was the goal, and having a long cycle of length n or root n was bad for me. So now this theorem guarantees that if you ensure that your graph is minimum degree 3, then there is a short cycle and you can find it fast. Okay. Again, this is a very simple proof, just essentially like a 2-line proof. So that's why it's pushed to the problem sheet. Maybe if there is time, we can come back to it. So now, and can be found in some m plus n time. Any minimum degree graph. Okay, so now we can go back to our old strategy of branching. So what do? I just apply these rules of dealing with degree 0, 1, 2 vertices. Graph is minimum degree 3. Then I am guaranteed a cycle of this length. Find that cycle and branch. Because once I find that cycle, I know that that has to be covered. Okay, because all the reductions ensured that a k-size solution here corresponds to a k-size solution here and vice versa, because that's the correctness of the reduction. So now I have to find a k-size solution here and I have to cover this cycle, find this cycle and branch. So I know that this has to be there in the solution, that has to be in the solution, and so on and so forth. And depth of height would be k, and what would be my branching factor? 2 log n plus 1. So what would be my running time of the whole algorithm? It will be like O star, so basically some or it will be order m plus n, but it will be something like a log n power k, because log n is, I put in big O, it's like some 2 log n, 3 log n, and the height is k, and I have a running time of this time. Okay. Is this a kind of algorithm running time we want? Does it fit into my? It's not, because what do I want? I want f of k times some polynomial in n, but this is not f of k, there is a log n there. See, we had 2 power k, we had 3 power k, we had you'll always have that n sitting here. Okay. So there is a second problem in the problem sheet which tells you that this running time is actually okay. It is of the type I want. Okay. So that is a problem in the problem sheet, that this function log n power k is still okay. It's reasonable. I mean, ideally we would like it to consider it as an f of k kind of thing. It doesn't look like it, but you can do some upper bounding to prove that it is actually of the type you want. Okay. So that this theorem proof and the fact that this is actually of the type we want, both are pushed to the exercises, because for the rest of the lecture I am going to actually give a different algorithmic technique and use feedback vertex set as an example and illustrate that technique, because that's another cute algorithmic technique. Okay. So we will design another algorithm for the same problem, moving away from branching. Clear? Questions? All right. So that takes us to this algorithmic technique called iterative compression. Okay. So let me try it on vertex cover first, and then we will come to feedback vertex. So what is the idea here? So suppose, so again you have a graph G and an integer k, and you are looking for a solution of size k. The solution could be vertex cover, solution could be feedback vertex set, but let me just say something more generally, and then we will instantiate to vertex cover or feedback vertex set. So suppose I give you a solution of size k plus 1. So I am talking about a special problem. Okay, so now I ask the same question. Does there exist a solution of size k? Okay, I have simplified my problem a little bit now. Okay, so you have given a graph where I am trying to find something of size at most k. It could be vertex cover, it could be feedback vertex set. We will try both. But in addition, I will make life simpler for you and give you a solution of size k plus 1. Now I ask you, can you find and detect whether there is a solution of size at most k? And then I will come back to addressing the question of who gives me this solution of size k plus 1. Okay, we will come to that later. Okay, so let's take vertex cover. Okay, now I want to design a fixed parameter tractable algorithm for this special problem where you are also given a k plus 1 size solution. Okay. So you are given a k plus 1 sized, let's say, vertex cover. This is the rest of the graph. And if this is a vertex cover, what do I know about this part of the graph? Independent set, right? There are no edges, so it's looking like this. Okay. So now I'm asking, is there a solution of size at most k? Okay. You want to design some algorithm. So now we can apply this technique where I discussed for minimum vertex cover in forest plus k. Remember that had a structure like this. We had a forest here, and then some k vertices here, and we did something to find a minimum vertex cover. I'm going to try something like that here. So that means now it's not a forest, but you are given a k plus 1 size set, and here the rest of the graph. If you recall that algorithm, how we proceeded, we will simulate that kind of an idea here. What did we do, if you remember? Yes. Yeah, so we guessed. I'm looking and testing for a solution of size at most k. I will guess its intersection with this. So, let us call this as a modulator, right, M, and say that the solution I am looking for, suppose it intersects M with this set Y. Okay, I do not know why, but I am going to try all possible values of Y. Then life actually becomes much simpler here. So, suppose I decided that my solution's intersection with M is Y. What all can you immediately conclude? That this side, what can you say? It's independent. It cannot have edges, right? Because if it has edges, who is going to cover them? Okay. And then what else can you say? See, remember there are edges like this. All kinds of, so this side is independent, is we checked. Our goal is to cover all these edges. So, neighbors of, exactly, good. So, we just pick neighbors of M minus Y, that covers all the edges. That is the end of the story. In the earlier case, what we had here was a forest. So, we deleted and found a minimum vertex cover in the forest. But here that is it, because there is no other edges. Where are the edges? Why? The edges are only across or inside, of course, because this is independent. This side is independent. There are edges inside M or across. And in M, I decided to pick Y. So, Y covers a whole bunch of edges. I throw them out. I remove Y. And anything which is not in Y better be independent. If it is not independent, I move on to my next Y. If it is independent, I just pick all its neighbors here, and that is the end of story. I have found a minimum vertex. So, try all possible Y and you have solved it. So, how much time does the whole thing take? 2 power k plus 1, because it is the number of subsets of Y, right. So, simply try all subsets Y of M and your G of M minus Y is independent, and pick neighbors of M minus Y intersection V minus M in the solution. So, this is all a polynomial time computation, right. So, this is all a polynomial time computation. So, overall load in the whole algorithm is the number of subsets of M. For every subset of M, I am going to do some polynomial computation. The number of subsets of M, since M is of size k plus 1, is some 2 power k plus 1. So, in 2 power k plus 1, I have solved the vertex cover problem if you give me a solution of size k plus 1. Right? Remember, this is not the original problem. This is not, is there a vertex cover of size at most k? Yes, that is a question, but you are augmented with the solution of size k plus 1, then I can solve it in 2 power k. Right? So, now let us come back to who gives me this solution of size k plus. So, this is what is called compression. So, what I am given is a k plus 1 size solution, and the compression step is trying to compress the solution size to something smaller than whatever is given. Now, who gives me this k plus 1 size solution? It takes us to the iterative step. So, that is also a very nice cute step. No. Oh, okay, very good question. Where did we even ask for k and so on? So, what it is that what is my solution I have picked? I have got Y and I have got neighborhood of M minus Y intersection V minus M. Together I count how many I have got. If it is less than or equal to k, then I say yes. So, for every such Y I did not get less than or equal to k, then I say no, right, because we are trying all, basically we are actually solving the minimum vertex cover problem here, because when you run over all possible Y, then you actually get the minimum, take the minimum, that is a minimum vertex cover, and if it is less than or equal to k, you say yes, otherwise you will say no, right. So, actually good point. So, So find min size among solutions for all S, and if its size is less than or equal to k, return yes, else return no. Okay, so that's a complete algorithm. I guess a solution, and then life becomes simpler. Try all possible guesses, pick the minimum among them, and if I get a solution of size at most k, I say yes, I found solution. Otherwise, I'd say no. Yeah. How do I get the k plus 1 size solution? Is that the question? That is given, yes. Which is why. When I say guess, I mean I am using the word guess to say this y. The intersection of my solution with M.
So you are first finding a subset, choosing a subset y, and then you are finding a vertex cover that contains y.
Correct. Exactly. I choose a y and then find a vertex cover that contains y. Okay? And that is nothing but the neighborhood of this set along with y. And I look at this size, and if it is less than or equal to k, fine. Otherwise, I try y, and I am trying all possible subsets here, including empty set, that find a minimum vertex cover that contains that set y, and pick among them the smallest. And if it is of size less than or equal to k, I say yes, otherwise no. Okay, and so overall running time would be so it's O star 2 power k. Okay, but remember, this is not the original vertex cover problem. That also we can solve it in 2 power k, even better. But this is if I am given a k plus 1 size solution. Okay, I mean, the reason it will be interesting, I am using vertex cover as a case study. We will, when we move to feedback vertex set, you will understand the problem. Okay, because for feedback vertex set, we did not even have some C power k algorithm. Yeah.
In the first step, we are finding for all y. And then second, if its size is less equivalent, we
Right.
should add neighbors also.
Yeah.
Current slide.
Neighbors of?
Neighbors of m minus y.
Yeah, that's what we are doing.
Down.
Yeah, okay. So let me be more precise. I'm just doing some hand waving. So let's say my solution S is y union neighborhood of m minus y intersection b minus m. So here you are saying,
Kind of yes.
yeah. Yeah. Okay, so now who gives me the solution of size k plus 1, right? Because you need that to solve this. Now there is a very cute way of getting that, and that is the iterate part of this technique. So iterative compression. So we've done the compression, we will do the iteration and get you, and put together we will get the algorithm for the original problem, the vertex cover problem, and then we will try and simulate this for feedback vertex set, right? So the usual difficulty for vertex cover, life was simple once we made a guess, because you just have to go and pick the neighbors. For other problems, it is not as simple. In particular, for feedback vertex set, this part is the hardest part. The rest of it is just like a template, you can use it. Okay? So let's ask, how do we get okay? So now you're given this huge arbitrary graph on n vertices. Now, can you give me a k plus 1 sized solution for some subgraph of the graph? So, let us say the vertices are 1 to n. Okay. I really want a k plus 1 size solution for the original graph. If you give me, I can solve my question in 2 power k time. Okay. But I don't know how to get the k plus 1 size solution. But now I am asking a question for some subgraph of the graph. Can you give me a k plus 1 size solution? That's all very clever. I don't want clever stuff. Simple stuff. Yeah, can you give me a subgraph of this graph? No. So what is the subgraph you want to give? Huh? Take some k plus 2 vertices. Right? The number of vertices is n. Take some k plus 2 vertices and look at that induced subgraph on them. Can you give me a k plus 1 size solution? Yeah, sure, right? Remove one and you'll get everything else, right? So what we'll do is the following. Let's call this as gk plus 2, which is the subgraph on vertices 1, 2 up to k plus 2. So here is my graph on k plus 2 vertices. This is gk plus 2. So I just delete this k plus 1 vertices. Give me a vertex cover for this special graph, this subgraph, right? Because it covers all the edges. If you remove it, there is only one vertex, right? So now on this graph, I will apply my compression algorithm. Remember my compression algorithm, if you give me a k plus 1 size solution, it will come back and tell me for any graph whether there is a k size solution in some 2 power k time. So on this graph, I will ask that compression algorithm. Can you tell me whether there is a k size solution, right? Two possibilities, it says yes or maybe it says no. If it says no, what can you say? So, I have to solve my original problem on the whole graph. Remember, that's my task. So, I've started in my original graph, I want to know whether there is a k size vertex cover. That's my original problem. So, I picked some k plus 1 size solution and run my compression algorithm. It comes and says, I can't find a k size vertex cover in this graph. What can you conclude? The whole graph also does not have a k size vertex cover because I can't even cover all the edges of this subgraph here. So, if the answer is no for this subgraph, then return no and stop. Right, for the original graph. There is no k size solution. Suppose it gives me a k size solution, k sized vertex cover. Okay, so it says, here it is. You don't need this vertex also. So I give you a k size solution that covers all the edges in this graph, right? Now what I am going to do is include one more vertex in my graph and also in the vertex cover. So now I look at this gk plus 3, include k plus 3 vertex into my graph, include that also into the vertex cover. Now remember, now I have a k plus 1 size solution for this slightly larger graph. Apply my compression algorithm. If it says no, I stop. If it says yes, I got a k size, include one more vertex. So how many times I may have to apply the compression algorithm? Some n minus k times. End of story. Right? Do you understand the whole algorithm now? Isn't it cute? Right? So it is like, if you give me a k plus 1 size solution, yes, there is some structure which I can make advantage and design an algorithm. That's the simpler part of it. Now, how do I use that to the original algorithm? We iterate, right? Start with some k plus 2 sized graph and apply my compression there. Can I get a k sized vertex cover there? If it is no, I say no for the original graph. If I got a k sized vertex cover for this graph, I extend my graph by one more vertex and add that vertex also in the vertex cover, because then I have a k plus 1 sized vertex cover for this slightly larger graph, run the compression algorithm, keep doing it. If any point of time I get a no, I will say no. If I keep getting yes at the end of it, I have a k-sized vertex cover. Is that clear? I mean, writing all this formally will be a mess, but I can repeat if something is not clear. Is that clear? Yeah? This iterate and compress, right? Enlarge one vertex into the solution and the graph and run your compression algorithm, keep doing it, and overall, now running time will be 2 power k times n or n minus k. Okay. For feedback vertex, for vertex cover, it's no big deal because we already know better algorithms even without all this, but I will now demonstrate the whole thing for a feedback vertex set. Okay. There, the compression step is much harder. It requires a lot more work. Clear? Okay. So I'm going to just say iterate by including vertex k plus 3 in graph and vertex cover. And that's continue basically, right? So overall, power k, or more precisely order 2 power k. There will be a factor of n here with whatever. Okay, now let's try this, because for feedback vertex set, remember we did not have a good FPT algorithm at all, because all we said is the cycle length can be very large and we have a problem. Okay, we can make minimum degree 3, which gives you log n and log n power k, but log n power k you will see is more like some k power k. Okay, that's the problem sheet. Now, but using iterative with compression, we will get some nice cute 5 power k algorithm. Okay, it uses like iterative compression and some branching. Okay, so what is the compression step? So your input is your G, V, E and parameter K, and there is an M which is a feedback vertex set of size K plus 1. So I am augmenting you with a solution of size k plus 1. Now I am asking, is there a feedback vertex set of size at most k? Right? So let's look at a picture. So this is M, this is a k plus 1, and this is the remaining graph. What can you say about this graph? In this case? Forest. It's acyclic, because this is a feedback vertex set, means by definition it covers all the cycles, but when you delete it, what you get is an acyclic graph. So this is a forest. Okay, so which means that it's like a bunch of trees here. So the iterate step is exactly as in the case of vertex cover. Okay, I may not, if I have time, I'll go over it, but rather you don't need to go through it, because who gives me a k plus 1 size solution? I do the same thing. I start with some k plus 3 sized graph, where a k plus 1 size, any k plus 1 size would be left with an edge or something. Okay, but if you are working with the multi-graph, pick a k plus 2 sized graph, any k plus 1 size set of vertices will be a solution, right? Because what is left would be a single vertex. Now run the compression algorithm on that. You get Either you get no or you get an S answer. If you get no, that means that I am not able to cover all the cycles on this subgraph with k vertices. There is no way you are going to cover cycles of the whole graph with k vertices, so you will say no. And if you get an S, you get a k size solution, add one extra vertex to the solution, one extra vertex to the graph, keep iterating it, and overall you will have an algorithm if we solve the compression step. So this problem is not easy. We are going to do it now. For vertex cover, this problem is trivial, but we will spend our time next few minutes on this. But all I am saying is if you solve this, you actually have solved the original problem with a multiplicative factor of some n. You have to do this compression. Is that clear? Yes? I am asking the TAs. Yes? Okay, because you are sort of benchmark. If you don't follow, then I have a problem. Right. Okay, good. So now let's spend time on the compression step, right? We're going to come up with some rules for this now. So again, another template we will do is guess the intersection of my solution I am looking for with M. The number of guesses is of 2 power k, so I can afford to do this. So let me guess, right? So suppose y is S intersection M. So S is my solution I am looking for. Okay, I will try all possible y's. So much of the template we can apply, and then there will be a crucial step where we need to work hard. Okay, so I am saying that solution, I am looking for a feedback vertex set, a subset of vertices that cover all cycles. Suppose I say that it intersects M at this point. Then what can you say about the remaining M minus Y? It must be acyclic. It must be a forest. It cannot have cycles because if it has cycles, who is going to cover those cycles? Okay, fine. So if it is not acyclic, you will try a different guess, different Y. Okay, so let's delete this. Now let's again look at the picture how it is. You have this is M minus Y, whose k plus 1 minus cardinality of y, so it's exactly equal to. And this is again a bunch of trees now. And this is V minus M, again it's a bunch of trees. So cycles are only across, and we want to pick small number of vertices from below to cover all cycles. That's the goal, right? Why only I need to pick from below? Why not I pick from above? No, but the cycles across are there. I'm going to cover. There are cycles across which I need to cover. Where should I pick from? I'm just saying, no, you can't pick from the top. You can only pick from the bottom. Why? Because I made my guess of my solution intersection with M. That means my solution does not intersect here at all, right? That's my guess. I made that choice. Why is the intersection of M and my solution I'm seeking for? And why I have deleted it? That means my solution is not there at all at the top vertices, right? If I can't find it, I'll try a different y and it'll get there, all possible y's. So at this point, the special problem I have is that I have a forest here, and a lot of edges across. So there are a lot of cycles, and my goal is to cover all the cycles by picking small number of vertices from V minus M. That's the goal. That clear? No. No. So let's just go back to the previous slide, right? So what did I do? Suppose I say y is S is the solution I'm looking for, and suppose S intersection M is this y. That's an assumption I'm making, right? I'm going to try all possible y's, so that assumption will go away, which means my solution is not intersecting here. The solution I am looking for is not intersecting here, because that's the assumption. That's all. That's all I'm saying. There's nothing much. So what is left? This is a forest because I can't pick anything from here. Who's going to cover those cycles? So there are cycles across, and my goal is to pick some vertices from V minus M to cover all the cycles, and ideally I want total size to be at most k, right? Exactly like the vertex cover question with this. So now let's come up with some rules. Okay. Suppose I have x is in V minus M has greater than or equal to 2 neighbors in one component of M minus y. Right? Suppose I have a vertex here which is adjacent to 2 neighbors of the same component. What can you say? Yes, so in the solution, that vertex x has to be in any solution of the solution I am looking for. Why? Because x is forming a cycle, and this cycle x is the only vertex sitting here. Everybody else is out there in M minus y, from which I am not allowed to pick any vertex anyway. Right? So in the solution I am seeking, x is the only vertex sitting here, so I have to pick x. Right? I need to cover this cycle. You need to cover all cycles. You need to cover this cycle, and this x is the only vertex which I am allowed to pick, because anything here I am not allowed to pick. I made my guess on the top vertices anyway. Is that clear? Yes? So pick x into solution, and k goes to k minus 1. So this is one rule. So I keep applying this rule. Okay, I keep applying this rule that whenever I have a vertex here at the bottom which has 2 neighbors to the same component, include it in the solution and drop my budget k, because it's sort of forced. Okay, that's it. That more or less we are end of the algorithm. So after this I am just going to do a branching, and this is where some clever thing that happens. So we keep applying this rule. We also, by the way, I forgot to say, we also make sure there is no degree 0, degree 1, degree 2. Anyway, you always do that, right? Because you can always pre-process it. But you have to be very careful. With degree 2 vertex, you have to be very careful. Okay? So suppose I had, suppose I had a vertex here which is degree 2. Earlier, what were we doing? Short circuit them. We removed it and added this edge. And what was the argument? Cycle will be preserved, and whatever x was doing the job, y or z can do. So if you want to pick x into the solution, instead now you can pick y and z into the solution. But now it's a problem. Why is there a problem? Because y and z are in the forbidden set, right? So just this degree 2 rule, don't do it. Every other degree 2 rule, so for example, if you have some degree 2 here, you can do that, short circuited, because this is in the allowed set. But if you have a vertex which has 2 neighbors up there and it is of degree 2, don't do that short circuiting. Modulo that, we will do degree 0, degree 1, degree 2 rules and make sure minimum degree is 3. And we also do this rule that if you have a vertex which has exactly or at least 2 neighbors of the same component, include it in the solution. We are done with all that. Now just one last step and we are done. And what is the next step? And this is the branching rule. pick a leaf vertex of a tree in V minus tree in V minus M. Let's call this some Z. We're going to branch like this. Include Z in solution or exclude Z in solution. That's all the algorithm. Okay, we're going to try like we did for vertex cover or cluster or something. All I'm saying, so here it's easy to justify because I just say I pick some vertex, I pick a carefully chosen vertex, and I say it is in the solution or it is not in the solution. I'll do some two-way branching. Okay. Because you are allowed to pick only vertices from V minus M. So I pick a vertex from V minus M, not any vertex but some careful vertex. And I say, okay, in one branch I'm going to include it in the solution, another branch I'm going to exclude it in the solution. So the correctness is not a problem because I'm trying whatever I'm supposed to do. As long as you are, you're not trying to be too clever, you try everything, then you don't have to worry about correctness. But analysis proof will have a problem now. Let's see. So far we have done only polynomial time, right? Because we have just said degree 0, degree 1, degree 2. We didn't do any branching. And if you have a vertex which is exactly adjacent to two neighbors, include it in the solution, drop k. These are all some polynomial computation. Now I am doing a branching here. So what happens to k here when I include z in the solution? K minus 1 because I picked up 1 in the solution. In this branch, k does not drop, which is a sort of a problem, right? Because all our analysis of our running time and branching algorithms hinged on the fact that in every branch k dropped, so your height is bounded by k. If k doesn't drop, then it can just remain like this forever, and you have no control on the height of the tree. Okay. So, but we will analyze it carefully and argue that something else drops, not k, but something else drops. And then it will put together, we will get a nice algorithm. Is the question clear? Is the problem clear? Is algorithm clear? Yep, you doubt? Okay. So, I mean, if k drops by 1 here and 5 here and so on, these are all good situations. But if k doesn't even drop, I have a problem. Okay, but the nice thing is it's correct, no problem, because I'm just trying whatever I'm supposed to do. Either S is Z in the solution or Z is not in the solution. Okay, so let's analyze this situation when Z is not in the solution. Okay, but pay attention to how I chose my Z. What I said is that this portion is a forest, it's a collection of trees. So go to a tree, pick a leaf vertex, and that is my Z. Okay. Now, how many neighbors does it have up there, this Z? What can you say something about it? Based on all the rules we have tried. Cannot have two, why not? No, only if two neighbors are in the same tree, we include it. So, can it have only one neighbor? Then it's a degree 2 vertex, right? Because it is a leaf in the tree. And if it has one neighbor there, it's a degree 2, I would have applied a degree 2 rule. So it should have at least two neighbors up there. If it only has two neighbors, then even if it's one vertex, if there's no edges here, I would be careful and not do anything about it. So the point is that Z has at least two neighbors in. So Z has at least two neighbors in M minus Y. Because otherwise, its degree would have been 1 or 0 or 2, and I would have applied those rules. Okay. Okay. See, in the case of vertex cover, the algorithm you came up with, either I include a vertex into the solution and so k drops, or you exclude a vertex, but when you exclude a vertex, you include something else. And that also implies k drops. That was a nice thing. Here, when I exclude a vertex, I don't know what to include because we are talking about cycles, not edges. Okay? So, what I am going to do is to put z in m minus y. Remember, m minus y is a forbidden set. You are not allowed to pick vertices from there, right? Because I made my guess and I said. So, m minus y is a set of vertices where I am not allowed to pick vertices. I can only pick vertices from below. So, in the branch where I am excluding z, it is equivalent to say I go and put z in m minus y. Right? Remember this picture. We are trying to cover cycles across by picking only vertices from below, because I made my guess here. So, that means these vertices are not allowed to pick into the solution. So, in one branch when I pick z, k drops. In the other branch when I say I do not pick z, I am going to put z in m minus y. Okay, now you will ask, so what? I mean, I want k is not dropping anyway. You put z here or not, you know, I am not able to bound. If I want to bound the height of this, some progress I should show, right? Now, it turns out, so if I throw some z here, can you point out that something else drops? Something nice happens in m minus y. That when I throw something, it is of degree at least 2. Yeah, what did it say? Somebody said something. See, huh? It's connecting components. See, its degree is at least 2. I argued that because of all the degree 2 rules and stuff. Its degree is at least 2, and the two neighbors are not in the same tree. Why? Because I would have again some other rule would have applied. I have picked it. So when I go there, it has at least 2 neighbors connecting 2 different trees. So these trees comes down. Number of trees in the top comes down. Okay. So if you think of a measure as not just k, because if I use k, then in one side it is dropping, in the other side it's not dropping. But I'm going to use my measure as k plus number of components in the top set. Then it is dropping in both directions. That gives you a bound on the height, because this k plus the number of components in the top is dropping at every step. So eventually it's going to go down. What is the maximum value for the measure? K plus the number of components in the top. Because the number of components in the top, remember, it is a k plus 1 sized set. So the number of components can be at most k plus 1. Okay, even if you ignore the y business. Okay. So if you take your measure as not just k, but k plus 1, the number of components, the 2k plus 1 is dropping in each of the branches. So the height is at most 2k plus 1 with a branching factor of 2. So the overall running time is 2 power 2k plus 1. That gives you a 4 power k algorithm. Okay. So this is this is not the first algorithm. For feedback vertex set, there are some 15 papers on feedback vertex set. This is something like 11th paper or something. Okay. And after this, there have been more things, but it's a very clever algorithmic technique, the iterative compression, and this branching step, it also conveys this idea of branching. When you branch, if you really want to measure the running time, k has to drop, but in this case, k is not dropping, but something else, some other progress is happening, which you can measure by using some other thing. So I should say z has at least 2 neighbors in y, and so number of components in m minus y drops by at least 1. So if you take my measure mu as k plus number of components in M minus y. Okay, so first of all, what is the solution size I am looking for now after I made my guess? So I made a guess, right? So I made a guess of y into the solution. Now I am looking for a feedback vertex set of size k minus cardinality of y, right? So it's not even so if I say, k prime as basically k minus cardinality of y plus the number of components in M minus y is also at most k plus 1 minus cardinality of y, then mu drops so the runtime is O star 2 power mu, but mu is at most 2k minus y but if you ignore all that, which is basically some 4 power k. Oh, this is for a fixed y. Okay, you should keep in mind. Once I fix y, then the remaining problem is something like 4 power k. Right? So let me just go over it again carefully. So once you fix y into my solution, I have a problem of a forest up there, a forest up here, and you want to cover all the cycles across by picking vertices from here. How many vertices I am allowed? K minus cardinality of y, because I already picked y, right? So this is one rule. If you have a vertex here which is 2 neighbors to the same component, I pick that vertex. Otherwise, what is below is just a forest, so everything has a tree, and each tree has a leaf, and a leaf has at least 2 neighbors. So pick one such leaf and say, I include x in the solution, or exclude it and put it z in M minus y. Since z has at least 2 neighbors in M minus y to different components, it connects 2 different components, so number of components decreases by at least 1. And so if I take the measure as whatever k prime I need to do, plus the number of components in M minus y, then this measure drops by at least 1 in each branch. So the runtime of the algorithm is 2 power mu, whatever the measure is. And mu is bounded by some 2k. That gives you O star 4 power k. And how many different y's are there? 2 power k plus 1 or something. So you multiply by that, that gives you something like an 8 power k algorithm. And this is for the compression step. And for the iterate step, you run through all possible, slowly expand it, and you have a multiplicative factor of n for it. Right? You start with a small graph where you have a k plus 1 size solution, do the compression in this much time, and then you expand it up to some n times. Okay? In fact, a more careful analysis of this, okay, so this is, so I might just say, hence it looks like 8 power k overall, but a more careful analysis okay. And there have been some 4 or 5 papers after this, including one I saw yesterday in arXiv, which improves this 5 to some 2.27 or something. So the race is currently still on. Okay? Not just on this problem, even for vertex cover. Okay? So vertex cover, there's been no improvement for about 10-15 years now. The current best, what's your name? Shashank will tell you an improved algorithm for vertex cover in the afternoon. In fact, he has figured it out. But the current best is something like 1.28 power k, and it's standing like this for about 10 years now. Okay, but the more improved algorithms are through more involved case analysis. It's all about branching. In this branch there will be a drop of 1. In this branch there is a branch of 5. Maybe you'll have 3, 4 branches. If the graph has this kind of a structure, you do branch like this, so it runs into some 3, 4 pages of case analysis sometimes. And so this is essentially the race in the FPT world, where you want to improve the f of k running time. And iterative compression is a very nice, powerful technique, which very much of the template you can apply, because you have to work on the compression step. You assume you have a k+1 size solution, guess the intersection of your solution with the solution given to me, remove that, and then the remaining graph. You have a lot of nice structure to play around. And once you've solved the compression step, you can iterate and solve the overall thing. Okay? And this has actually helped solve several open problems. This technique is about 10, 15 years old, and at that time several other open problems. The directed feedback vertex set problem was open, and this technique helped solve all that problem. So many of this is about 10 years old. In fact, as I said, fresh off the plate. There was one paper on undirected feedback vertex set, FPT algorithm, even one yesterday I saw. Okay, so I think I will again stop here. So we went through about 3 techniques for parameterized algorithms: branching, kernelization. Kernelization is also an equivalent definition of parameterized complexity. It turns out that a problem is kernelizable if and only if it has a fixed parameter tractable algorithm. And the third technique we saw is iterative compression. Okay? And try this for feedback vertex set, and you will get a little bit more exposure in the afternoon problem sheets.